Now we continue with our next discussion, that is methods to improve steady state stability. What are the methods? To improve the steady state stability. You know the power transmitted, electrical power transmitted, formula is EV by X sin delta. So first one is you increase the excitation voltage. Second one is increase the operating voltage. Third one is you decrease the reactance. How to decrease reactance? By using series capacitor, just now you did. And second one is, you know, by using bundled conductors, you did in the last week class. And third one is by using double circuit transmission lines. By using a double circuit transmission lines. So how a double circuit transmission line look like? Tower is the same. But this side we have three conductors of one circuit, and on other side we have three conductors of other circuit here. So this is how you represent a double circuit transmission line. So these are the methods to improve the steady state stability. Now we discuss the other classification, that is transient stability. So now the next one is transient stability. So when you come across transient stability for a short circuits or a three-phase faults on a transmission line. Suppose you consider this power system network of alternator, step-up transformer, so you provide the circuit breaker here. Now you deal with a three-phase fault on one of the parallel transmission lines. Three-phase fault on one of the parallel transmission lines. So indicate the three-phase fault now on one of the parallel transmission lines. So due to this fault, electrical power transmitted during the fault is 0. So how you define the transient stability? Definition is similar to steady state stability only. But at the end we change for sudden and large changes in load demand. So how you define transient stability? It is the property of synchronous machine to transmit maximum active power through the line by maintaining synchronism with externally connected transmission line. for large and sudden changes in load demand. For large and sudden changes in load demand. And how you write the power transmitted before fault? So the power transmitted, first to indicate before fault. So PE1 how to write? PM1 sine delta naught. And how much that PM1 is? EV by X1 equivalent sine delta naught. Next is the power transmitted during fault. PE2 how you write? PM2 sine delta is EV by X2 equivalent sine delta. What is X1 equivalent? The equivalent transfer reactance before fault. What is X2 equivalent? Equivalent transfer reactance during fault. So during fault, power transmitted will be less. So you write PM2 or PE2 less than PM1 or PE1. Now we check the conditions where power transfer during fault is 0. So conditions for which the power transmitted during fault is 0. First condition is you assume that fault has occurred on a transmission line near bus bar. Assume that fault has occurred on a transmission line near bus bar. Then you treat the fault as on the bus bar. So voltage at the bus bar same as fault voltage 0. So power is not transmitted during fault. So what is the first case? The occurrence of fault on a transmission line near bus bar. So how you treat it as? You treat it as fault on the bus bar. So voltage at the bus bar same as the voltage at the fault point 0. So the power transmitted during fault. How much that PE2 is 0. During fault PE2 equal to 0. The second condition is, say now a three-phase fault has directly occurred on the bus bar. A three-phase fault has directly occurred on bus bar. So due to that, what happens? The system is subjected to severe disturbance due to sudden changes in load demand and large changes in load demand. So second one is fault on the bus bar. When fault occurs directly on the bus bar, there is a significant disturbance due to sudden changes in load demand and large changes in load demand. So now how you find the significant variation in the rotor characteristics? By developing a dynamic model. So when fault occurs on the bus bar, the change in the rotor position with respect to stator, you say it as significant. And due to that, what happens? We have to develop the dynamic model. Dynamic means as a function of time. Dynamic means as a function of time. So now we develop the dynamic model to analyze the transient stability of the system. So now we develop dynamic model to analyze transient stability of the system. So to develop this dynamic model, obtain the mechanical equivalent of rotor here. That is, you provide the shaft here, here electrical output, input is mechanical, shaft torque, opposite direction we have electromagnetic torque. Opposite direction we have the electromagnetic torque. And what about the speed of the rotor? The direction of rotor same as this omega. It is same as that value. How much here? It is omega. Now first you consider stable operation. So we check the stable condition. So under stable condition, what is PA? Mechanical input minus electrical output is 0, or you say omega equal to omega s, or n equal to ns. So what about the rotor now? Neither accelerates nor decelerates. So this is case 1. For stable conditions, PA is 0. Or say this stable condition as before fault. You refer anything, case 1, that is before fault. Now we should check during fault. And during fault we know that electrical power transmitted decreases. So what will be PA now? Formula is shaft input PS or mechanical input PS minus electrical output PE. As PE decreases, what happens to PA positive? What about PA positive? Refers that the rotor accelerates. If rotor accelerates, omega greater than omega s or n greater than ns. Now how to find out that accelerating power? Accelerating power of rotor in terms of the kinematics of rotating machine is given as TA into omega. What is TA now? It is the accelerating torque expressed in Newton meters. What is omega? Angular velocity of rotor. How much it is? 2 pi n by 60. What is n? N is the actual rotor speed in RPM. N is the actual rotor speed in RPM. So say this as the equation 1. But how to write the accelerating torque? It is I into alpha. What is I? Is the inertia expressed in kg meters square. What is alpha? Angular acceleration of rotor. So you substitute this 2 in 1. So what is this PA now? I alpha into omega, or you write I omega into alpha. What is I into omega? It is m. What is m? The moment of inertia. What are the units to express megajoules second per electrical degrees, or you write megajoules second per electrical radians. Now we will work out on what should be PA now further. Further, what you do is you consider the position of the rotor with respect to the stator. Consider the position of the rotor with respect to stator. Say this is the rotor axis, here the stator axis. What about here the reference axis? So what is the angle between the rotor and stator? By default you mention delta of t. What about this angle? You say gamma of t. And now between the rotor and the reference you mention it as theta of t. So from this figure what we understand, theta is sum of gamma plus delta. And what is gamma? Angular distance between stator axis and reference axis. And how you write this gamma of t? Omega r into t. What is omega r? Omega r is the relative speed between stator axis and reference axis. So from this what you write now? Theta, it is delta plus gamma. So differentiate first with respect to t, d delta by dt, and how much gamma is omega r. So differentiating this omega r into t, how much you get now? Omega r. Now you differentiate once again. So you mention d square theta by dt square is d square delta by dt square. That is the angular acceleration alpha. So now this equation 3, 4, you substitute in 3. So substitute 4 in 3 now. So what is PA now? M into d square delta by dt square. From this you write what is d square delta by dt square. It is 1 by m PA. So what you write that PA as now? Mechanical input PS minus electrical output PE. So lastly, we substitute what is that PE now. What you substitute PE as? EV by X sine delta. How much it is? EV by X sine delta. And what you call this equation 5? Swing equation of synchronous generator. So what you call the equation 5? You call it as the swing equation of a synchronous generator. Now observe two important points here. As the load demand changes, the position of rotor with respect to stator changes, but the position of stator with respect to reference axis do not change. I repeat, as the load demand changes, the position of rotor with respect to stator changes, that is delta changes, but the position of stator with respect to reference axis do not change. Therefore, we always consider stator axis as reference axis. We always consider stator axis as the reference axis. Now observe the swing equation. It is a second order non-linear differential equation. And what does the swing equation signifies? It determines, delta means the position of rotor with respect to stator as a function of time. For how many cycles? For the duration, the system is subjected to sudden and large changes in load demand. Sudden and large changes in load demand. So what is the significance of swing equation? Swing equation determines the change in the position of rotor with respect to stator as a function of time for a specified number of cycles during which the system is subjected to sudden and large changes in load demand. Then what about in the case of synchronous motor? Same way we represent. You get equation 6. So d square delta by dt square is 1 by m. Their electrical input is EV by X sine delta minus mechanical output is PS. This is the swing equation for synchronous motor. This is how you represent swing equation in case of synchronous motor. So swing equation is not only used in the analysis of transient stability, but we also use swing equation in the analysis of steady state stability. What for? To find the frequency of rotor oscillations for small and gradual changes in load demand. So swing equation is not only used in transient stability analysis, but also used in steady state stability analysis. What for? To determine the frequency of rotor oscillations for small and gradual changes in load demand. For small and gradual changes in the load demand. So now we check analysis of steady state stability using swing equation. So our next topic is analysis of steady state stability using swing equation here. Now for our analysis, you consider an alternator, show its reactance, connected to line further to an infinite bus bar. So here how much E at angle delta, here it is V at angle 0. Now what is the difference between infinite bus bar and finite bus bar? Finite bus bar you have drawn earlier, say alternator, step up transformer, further lines like this. All these are finite bus bars. In case of finite bus bar, only frequency is constant, whereas voltage is not constant. But in case of infinite bus bar, voltage, frequency both are constant. Now initially, say the mechanical input is PS, electrical output is some PE naught. So case 1 you consider is before increase in load demand. What about PA? Mechanical input minus electrical output, both are equal 0. PA 0 means, what about rotor? Neither accelerates nor decelerates. So omega is omega s, n equal to ns. Now we have the case 2. After increase in the load demand, so how much the load demand has increased, you don't know. Assume that it is delta P. So now we apply the swing equation. D square delta by dt square is 1 by m Ps minus earlier Pe naught, now it is further added, you get delta P. So on simplifying this, how much you get? These two terms are equal. You get minus delta Pe by m. Are you right? Md square delta by dt square plus delta Pe is 1. So observe the equation 1. It is a second order nonlinear differential equation. What about the equation 1? It is a second order nonlinear differential equation. How to convert to linear differential equation? Use Taylor series of expansion. For that we use Taylor series of expansion. How to write this one? Md square delta by dt square plus dou Pe by dou delta evaluated at initial delta angle must be represented here. So this is how you represent using the Taylor series. So in Taylor series we make use of the partial derivatives. Now you take out that delta outside and check what is the frequency of the rotor oscillations. And also we mention in the case 1, what is this angles now further? How to represent this further now? In the case 1, how you represent further the swing equation? D square delta by dt square. How much? 1 by m. If you want, you include mechan Pa. How much this Pa is equal to? Ps minus Pe naught. Both are equal 0. So that means you mention that delta is same as delta naught, that is the initial load angle. Now we represent case 2. You can write this equation for case 1 also. And now we develop case 2. That is, after you increase the load demand. So initially Pe naught, now delta Pe is added. So what about Pa now? Ps minus of this value. These two being equal, how much you get? Minus delta P. Pa negative means what about rotor? Rotor decelerates. Pa negative means rotor decelerates. So omega will be less than omega s or n will be less than ns. Now, for case 1, PA 0. So what is the position of the stator with position of rotor with respect to stator? It is delta of t, nothing but delta naught. Now for case 2, when there is increase in the load demand, so you have stator here and here it is rotor. So how much delta is now? Delta naught. So due to increase in the load demand, what happens now? The rotor axis is shifted. What about the rotor axis? It is shifted. Say how much it is shifted by? Say some delta here. It is shifted by delta here. So how to write the swing equation now? D square by dt square. Initially delta naught plus delta equal to 1 by m PA. But how much that PA you got here? Minus delta P. But always you observe one point. Before you increase the load demand, what about the rotor angle is constant? As long as there is no increase in the load demand, the load angle delta naught is constant. Only when there is increase in the load demand, delta naught increases further to delta naught plus delta there. Delta naught plus only this one is delta, small portion. So I repeat these steps once again. You know that swing equation is used for analysis of transient stability. But you can also use the swing equation to analyze the steady state stability. That is, to find the rotor oscillations for small and gradual variations in load demand. Small and gradual changes in load demand. For that you consider an alternator connected through the line to the infinite bus bar. First to consider the case 1. Before the increase in the load demand. So mechanical input same as electrical output, initially PE naught. So PA is 0. So rotor neither accelerates nor decelerates. Omega is omega s or n equal to ns. So d square delta by dt square is 1 by m PA. How much it is? 0. So delta naught is the initial load angle which remains constant. As long as there is no change in the load demand, delta naught remains constant. I repeat, as long as there is no change in the load demand, the load angle delta naught remains constant. And now you consider, after increase in the load demand, you say that load demand is increased by delta PE. PS PE not equal, so PA is minus delta PE. PA negative means rotor decelerates. Previously equal to omega s or equal to ns. Now less than omega s or less than ns. Now you draw the positions of the rotor with respect to stator. Before increase in the load demand, delta naught is constant. After increase in the load demand, you have the new position of rotor displaced by angle delta here. Now as this delta naught is constant, what will be its derivative? 0. If its derivative is 0, we write only d square delta by dt square. And what about this side? Minus 1 by m delta p. Take that to the left hand side. D square by dt square delta plus 1 by m delta pe is 0. Now this equation 1, you observe, is a second order nonlinear differential equation. How to convert to linear differential equation? By using the Taylor's series. So what you write? D square by dt square delta you represent m to this side now. Here dou pe by dou delta evaluated at initial angle delta naught multiplied with delta is 0. Now further you take out the delta common. So what you will get? md square by dt square plus dou pe by dou delta evaluated at delta naught multiplied with delta is 0. Now how to satisfy this equation 2 now? You are having the product of two terms. One should be definitely 0. Now is this delta 0 here? Not equal to 0. So only option left out is satisfying equation 2. What it is? md square by dt square dou pe by dou delta is 0. Now you say this d by dt as k. So how much? mk square plus dou pe by dou delta equal to 0. From this you find out what is k now. So you get minus dou pe by dou delta evaluated at delta naught. So k square is minus 1 by m dou pe by dou delta evaluated at delta naught. What is k now? Apply under root here. Plus or minus 1 by m dou pe by dou delta evaluated at delta naught under root. And what does k gives? The frequency of rotor oscillations, and that is what we have to determine here. So we are finding the frequency of rotor oscillations, and this equation you name it as characteristic equation of steady state stability analysis using swing equation. Second order characteristic equation of steady state stability analysis using swing equation. Now you deal with different conditions now. First condition you mention as dou pe by dou delta is positive. This is positive. If it is positive, what you will have? You are taking the square root of some negative terms. if you take the square root of some negative terms, say minus 9, what is square root of minus 9? You write plus or minus j 3. So what about the nature of the roots? The nature of the roots are imaginary. So with non-repeated roots on j omega axis, what about the system? The system is marginally stable. Or you say the system is undamped. The system is undamped. So what about the system? You say it as marginally stable, or you say the system is undamped. Now you refer the condition to, say now dou P by dou delta is negative. Already you have negative sign. This dou P by dou delta is also negative now. Negative, negative, how much? Positive. So you are taking the square root of some positive term. So where you will get the roots? They are real and symmetrical with respect to imaginary axis. So one root to the left, one root to the right. Suppose this total is 9. What is the square root of 9 you get? Plus or minus 3 here. So what about the system now? Unstable. The system is now unstable. So always to make dou P by dou delta positive. That means delta must be always less than 90 degrees. You know this point. For this, delta less than 90 degrees and here delta greater than 90 degrees. Now, though you have imaginary roots, you know in the yesterday's session we did the windings of alternator. Apart from armature winding, field winding, you also have a damper winding. So you say though the roots are imaginary, the roots are provided with damping effect. The roots are provided with the damping effect. So this is the analysis of steady state stability using swing equation. The analysis of steady state stability using the swing equation. Now we refer the next important terms in stability, that is inertia constant h. How to write the inertia constant h? It is kinetic energy stored by rotor divided by volt ampere rating of alternator. So what is kinetic energy stored by the rotor? Half I omega square. Volt ampere rating, you write it as some h. Now you simplify this. I omega, write separately the omega. This omega you write it as 2 pi f. 2 gets cancelled. I omega is m. So on simplifying, what is m you get? sh by pi f. What are the units for m? Electrical megajoule second per electrical degrees, if you write pi as 180, or megajoule second per electrical radians, if you write pi as 3.14. Now second one is, in the formula of percentage reactance, we have written base MVA by kV square. So how percentage X is related to MVA? But here how H is related to volt ampere rating? Inversely related. From this two, what you conclude? Percentage H and percentage X are inversely related. From this two, what you conclude? Both are inversely related. Okay. Now you have 5 minutes break.